All right. So today we are going to do I don't have any slides for you. We're going to be doing just some board work. We're going to talk about how we think about designing with hydrologic data and statistical analysis. So design hydrology or hydrology and design. Okay, so our learning objectives are going to be one, to discuss methods for designing, i.e. sizing. Please stop. Oh boy, this is going to be i.e. sizing hydraulic structures. Who can think of some hydraulic structures that we might want to design and use hydrologic data? What's that?
Like weirs or
Weirs, dams, culverts, anything that hydrology needs to move through. And what is hydrology? Well, it's typically runoff from rain that we're talking about. So conveying water. We will explore, oh, this is gonna kill me here. Different risk-based design standards and approaches. We'll just say design approaches. There's different ways to think about risk in hydrology, so we'll talk about that. And then we will apply basic statistics to calculate risk and design features. So this is going to set up the kind of basis for what's the kind of framework for how we approach design in hydrology. And we'll talk about specific instances and cases and applications as we move ahead and learn more about the context and the content. All right, so. Okay, so let's just talk about the basic premise of engineering hydrology. And really the basic premise is that we want to be able to predict peak discharge rate. This is not the only variable we want to know, but it's often the most important. So we want to be able to predict peak discharge rates and synthesize discharge hydrographs. A hydrograph is simply discharge, sorry, this should be time. Time and discharge, and so it's just discharge over time. So we want to be able to basically synthesize, which means fabricate or make up these discharge hydrographs, because often we don't have observations of flow in a particular area. So we have to come up with a way to make these up so that we can understand how much flow we'll have over time, how much volume. If you integrate under this curve, you get volume. And that can help us with sizing something like a pond, a reservoir, stormwater detention structure, something like that. And we want to use this to design hydraulic structures. Okay. And so we talked about some examples. Well, a really big one that we didn't bring up is a stream crossing. Stream or river crossing, right? So this could be a bridge, could be a culvert. I was talking with CDOT, Stuart Gardner recently. He's a CDOT hydrologist here in Grand Junction. And you know, they have thousands of culverts under their roads. So you just think about Highway 340, which goes past the monument on the way to Fruta, past through the Redlands. So that's a state highway. South Broadway turns into South Broadway. And that thing crosses, like, how many little tiny gullies and washes and canyons does that thing cross, you know, over the 10 miles? Hundreds of them. So the senior design project last year, one of them was redesigning a culvert for one of those canyons. And that was like a bigger project, bigger design project, but you got to be able to convey water through roads, and especially in arid regions like here, there's just innumerable amounts of these. And some of them you want to spend more time on designing because it's going to be a big, you know, 10-foot diameter culvert. Some of them, it's a tiny drainage and you need to deal with the water because you can't have a pond on the road, but you're not going to spend, you know, hours and hours and hundreds of thousands of dollars designing and constructing it. So we'll talk about different approaches based on the risk and the consequence of a failure. So this could also be stormwater. So anytime you design, and this is conveyance, so curb and gutter, stormwater sewers, as well as detention or treatment. So any sort of development that you have is going to have to deal with stormwater. When it rains, how much water will you have? What's the peak discharge rate? Where can it go? And how do we have it so that it doesn't impact the folks downstream? Yeah, no worries. And then kind of in big picture, we have dams and spillways. So these are kind of much bigger infrastructure projects, more design and probably less risk tolerance there. Can you guys think of some others just that we might have in the Grand Valley where we need hydrologic data to design infrastructure?
Irrigation canals.
So we have, I didn't talk about reservoirs specifically, but when you want to design a reservoir, typically these days, we don't build new reservoirs. Maybe we augment or expand the reservoir by building a higher dam because we need to store more water, maybe because we have less precipitation. There's a lot of hydrologic analysis involved in that. How much do we want to store based on our demand? How much do we have available, and what's the risk of it going dry? So reservoirs would be a big one. Anything associated with irrigation out here, right? We have this huge canal system, and we need to be able to understand how much water we can get into it, which could be a hydraulic question. It could also be a hydrologic question. Okay. And Dylan, I'm recording this, so you can always go back and get caught up. So the idea here is the basic premise of engineering hydrology is to predict peak discharge as well as discharge hydrographs, which is discharge over time. Okay, so let's talk about different design methods. And there's kind of different approaches that we can use and based on different data and statistical methods. So the first one we could think of is flow-based. And this is where we have a flow record. Or we could use regression equations. And remember, regression equation could be something where we have an explanatory variable and a response variable. Maybe this would be Q peak, and maybe this would be drainage area for your upstream watershed. And maybe there's some sort of line you can fit to that relationship. So we could have regression equations, and this would be based off of USGS gauge data. We're going to be talking a lot about USGS gauge data, US Geologic Survey, and then they have this network of stream gauges across the country in Colorado. So they collect data, and we can use it to inform a lot of things. So maybe we're designing something on a river that actually has a USGS gauge. Did anyone look at USGS gauge data for their discussion?
You might have fine on it.
All right,
Yeah.
check it out, let us know. So, you know, that's a really important source of data that we have. But in order to use an actual flow record, our design project, maybe it's a bridge on the Colorado River or something like that, it needs to have a USGS gauge somewhere nearby, right? So for that data to be valid. There can't be like a major tributary coming in like the Gunnison River, which is a problem for the South Broadway Bridge because we don't actually have gauge data between upstream of the Gunnison and downstream of the Gunnison confluence. So it's often rare that you're working on a system that has a flow record. So we often rely on, if we want to do flow-based, we need to have some sort of regression equation that can say, okay, we took a bunch of data from other stream gauges in the area, and we're going to apply it and calculate some design variables for our own site based on some independent predictor variables. Okay, we'll talk about this concept in a minute, but we did it in statistics. So we talked about the 1% annual exceedance probability flood. So this is AEP. And Jake, since you didn't have the benefit of doing the application here in statistics, the annual exceedance probability flood is just the flood that has a 1% chance of happening in a given year. It sometimes is referred to as the 100-year flood, but that is misleading. So we're trying to get away from that nomenclature. Because we're dealing with flow data, if you were to run statistics and calculate the 1% AEP flood, it's direct, right? That's a direct estimate of the magnitude peak discharge of that flood event. Okay, we can also do precipitation based. And this is where we're bringing in the idea of rainfall runoff modeling. Which is exactly what we'll be doing for the project. Rainfall runoff modeling, we figure out how much rain we expect to have. And so in this case, you would do the 1% AEP precip depth. So how many inches of rain do we expect to have over a 24-hour period in this particular area with a 1% annual exceedance probability? So we need to come up with a design storm. What does that storm look like? How much rain happens? What is the kind of temporal signature of rainfall over time? And we'll get into precipitation design storms and that sort of thing starting Thursday. There's also this idea of storm transposition. I'm just going to introduce the concept. We're not going to do this. So is anyone, you're probably familiar with looking at the radar during a rain event. We haven't seen rain on the radar in a long time, but you may remember what rain looks like. And there's a, there's kind of like a contour, right? It's like a color map, and maybe it's like super purple in the middle, and then it's like green on the outside. Well, we have great radar data, which tells us basically how much precipitation is in a cloud, how much rain could come out of this cloud. And then we can calibrate that based on rain gauge data to see actually how much came out and met the ground. Well, we can take a storm event. So say we have this record, this radar record of this crazy storm event, like the September 2013 flood on the Front Range. And we can say, okay, over 7 days, this is what the rainfall looked like in terms of if these are like rainfall contours here. So maybe, we had 4 inches fall in the middle, 2 inches, 1 inch, 0.5, something like that. These aren't equal contours, obviously. So you could take that rainfall event and just say, I'm going to plop it over my watershed and see what happens in terms of the flood that would result. So that's what transposition means. It just means moving, transposing, moving it. And so you just take a storm event that happened somewhere and you move it and put it over where you are designing a dam or something like that. This is obviously pretty technical, and we only do this for kind of big infrastructure projects like a dam redesign or a dam construction, something like that. We want to say, okay, this massive flood event happened in this region. We don't have record of on our particular stream of what happened because it didn't fall there, but we'll dump it on my watershed and see what the flood response looks like. But you can't do this everywhere. I can't take a flood event from the Front Range and bring it over here at Grand Junction because the Front Range has different kinds of storm events than Grand Junction does. And so the Dam Safety Office in Colorado did this huge study with New Mexico, and they kind of came up with these regions called storm transportation zones or something like that. And the idea is that within these zones, you can take any storm event that happened and you can use it interchangeably in that zone. But I can't take a storm event from one zone and move it to a different zone. So it's like regions where you have similar kinds of storm events. Okay, so when we do flood events here, it's not like super direct, because if we do the 1% precipitation depth and then we get a hydrograph out of that, this peak discharge, is that the 1% AEP flood event? What do you think, Christian? So the answer is not necessarily. And why is that? Well, the flood frequency analysis of a particular stream that drains from a watershed that a rainfall event comes on is obviously related to the magnitude and frequency of rain that that watershed receives. But there's a disconnect between what we observe in rainfall frequency and what we observe in runoff peak discharge frequency. And the reason is for that, there's a lot of reasons. Watersheds are complex. Rainfall events might hit them in different ways. And maybe a rainfall event strafes it and goes by really quickly, but dumps a lot of water. Maybe a rainfall event goes all the way up the watershed. We'll talk about some examples of that. The quick answer is that the world is complicated and there's not a one-to-one relationship between rainfall and runoff. There's a non-linear relationship. So for example, the 2013 flood event in Colorado on the Front Range, the 7-day cumulative rainfall that came out of that flood event over Boulder and the Front Range was on the order of 1,000-year recurrence interval, or 0.01%. So really, really massive rainfall. But then you look at the flood peak record for St. Vrain River, for Big Thompson, Boulder Creek. The runoff, the magnitude of the peak discharge was on the order of a 100-year, 200-year event. In Boulder Creek, it was a 30-year event. So it just really depends on where the rainfall is falling, how much of it comes out in a particular area. So you don't get that 1% AP precip depth and then a 1% AP flood event. However, we do often, when we do rainfall runoff modeling, right here, we often make this assumption, and then we can make some conservative assumptions to say, okay, well, what would kind of the worst case scenario runoff event be for this if we got this precipitation event? So say, for example, the watershed was already soaked with water, the soil is saturated. It's anything that runs off of it or anything that rains on it will run off immediately like pavement, which is what happened on the Front Range. So when we do this precipitation-based method, which often we have to rely on because we don't have good gauge data, we're adding more uncertainty. Because it's indirect. Okay, so we'll continue our discussion about design storms. And then let's make some definitions here. So the 1% annual exceedance probability or annual chance. And we'll call it an event. Could be a rain event, it could be a flood event, it could be a drought. But we'll turn in terms of rainfall. So we'll say the definition is the maximum rainfall over a point. And that's important. We'll talk about what that means in the next lecture. With a specified duration, so that could be 24 hours, it could be 6 hours, something like that. That has a 1% chance or probability of being equaled or exceeded in any given year. Okay, this is the same definition we used as before in statistics, but we're adding a little nuance because we're talking about specified duration. And the idea is rainfall happens over space and time, and maybe we'll get a very short, intense rainfall event, a 1-hour storm. So what's the 1%, what's the depth associated with a 1% 1-hour storm? Well, that's going to be different than a 1% 24-hour storm, right? And then with points, the whole point of saying a point is that we're dealing with rain gauges. This is how we collect data for rainfall events. A rain gauge, you know, it's just a little bucket. And I'll bring one in, we can look at it. It collects the rain. It's got a little tipping bucket in it. And the drops go in here, it tips and goes this way. And then the drops go in here, it tips, and it goes that way. And every time it tips, there's a little computer attached to it, and it logs that event. And it says every time that bucket tips, say 0.01 inches of rain have fallen. And so it just does a timestamp associated with that. So that's pretty low tech technology, but that's how we collect rain data. And it's over a point. But obviously rain falls over a watershed, and what happens over a point is much different than what happens over a huge watershed. So we'll talk about that on Thursday.
Is that the most common rain gauge there?
Pretty much. I mean, there are like, if we probably walked down to the NOAA Weather Service Center here or the airport and looked at their weather station, we'll talk about different rain gauges, but they have some that'll measure just the weight of water, which is a little more direct. I would say this is the most common, like low tech, I want to go out and throw one up for a year. This is what I would use.
So is that one, because I mean, if it's all about the tipping, like the floods in 13, I mean, would it still tip or would it be a constant flow at some point,
Right, so it's gonna, yeah, so there's a maximum amount that I can record, so it can get saturated, overwhelmed, basically, because there's just a little orifice right here. But that bucket will tip, and if it's tipping every second or every half second, like it'll record it. Okay, so we get our data for this from, well, I'm going to skip this part because we'll talk about it later. But we get this data from NOAA, which is the National Oceanic Atmospheric Administration. NOAA. I like NOAA because it's like Noah's Ark. Not spelled the same way, right? But they give us the data on when we have floods. Okay, and then let's look at just some more aspects of this. If we have a smaller watershed, a shorter duration storm will typically have a higher peak discharge because you can have a really intense storm and all the water can move really quickly to the outlet of the watershed. If we have a larger watershed, we need a longer duration storm to have a higher Q peak. And that's because it's just bigger and it takes longer for water to move. And so you basically have to keep dumping water into the watershed in order for it to kind of saturate and maximize the peak discharge. Okay, so just another note on the 1% storm does not equal the 1% flood. But sometimes we assume it does. So why is that? Watersheds are complex. The duration of the storm is important. We could have what's called watershed storage. And think of this as the soil moisture prior to storm. If we have a real dry, thirsty watershed, it might soak up a lot of the rain. We could also have a fire. So we got Grizzly Creek fire, we got Pine Gulch fire. Say I calculated Q peak coming out of Grizzly Creek. There's actually a USGS gauge there, so we'll have to look at that data. Q peak for Grizzly Creek for the 1% AEP based on that gauge data. Now they had a fire. Is that data valid? Am I going to have this, if the same rain falls over that watershed, am I going to have the same peak discharge coming out of Grizzly Creek? Why not? Do you think, Edgar?
Probably just not enough water reaching like that. You're just not enough like water that's going into like the runoff. Like the fire's probably
The fires, yeah, like if it's burning, right? Yeah, maybe the fire would just evaporate the water. But if we get a big dump on a watershed that just burned, you're gonna get that burned soil is hydrophobic. It's gonna repel the water for maybe 3 years before it'll infiltrate it well again, like it did before. And so you're gonna have massive floods coming out of there, mudslides, debris flows. It's gonna be a nightmare if they get a big rain event. And very sad for Grizzly Creek. Okay. Let's talk about frequency analysis. And if you took stats, you have done this already. Where this is, so we'll just say this is kind of an approach for design. And the idea of frequency analysis is that we want to identify a minimum acceptable frequency of an event, i.e. a failure, in a given year. So we talked about the 1% chance flood. Well, often when we're designing things like small culverts or something like that, well, the 10% annual chance flood might be okay. So what happens if a culvert, so say we design the culvert to convey the peak discharge associated with the 10% annual chance flood. All right. So on average, we have about a 10% chance of that culvert of a flood happening that the culvert cannot convey. What's the consequence of the culvert not conveying flow? Val, what do you think?
Just like overflow on the one side that the water's coming from.
So we might get some water on the road, right? The road could be flooded. If it's really bad and a culvert is overloaded, you could have water going like, so here's our culvert. Here's our roadway. And so the water is kind of spilling over and it's coming down, and say this is not armored, you could actually kind of scour this out and the roadway could wash out, right? That could be bad. Or you could scour out down here and this could fail. So depending on the flood events, maybe the whole crossing could fail, but you could also design for that too. So maybe it's expensive to put in a culvert that conveys the 100-year or the 1% chance flood. So we'll do 10. And then maybe we'll just design the road so that if it gets overwhelmed and it's really important that it doesn't wash out, it's okay if it's flooded for, 6 hours or something like that, then we can design the road to not fail when this culvert's overwhelmed. So we can kind of mitigate that risk, but save ourselves some money because culverts are expensive. So the frequency analysis, we went and identified this kind of inherent risk tolerance, and we're not calculating risk, we're just calculating the probability here. So 10% is pretty common for culverts on like small roads, like neighborhood roads, residential roads, or county roads. Ditches, so water going under ditches or something like that, trails, that sort of thing. So low consequence. Then we have our 1%, which is often as a common thing, and that's going to be the design frequency that we're going to use for major roads, so like an interstate. Or maybe critical infrastructure. Infrastructure. There was a flood control dam facility that was constructed off of I-70 in Bosley Wash. So you probably saw it under construction over the last couple of years. It's just basically a big berm with a gate and a kind of outlet control on it. They designed that to retain, I think, the volume of the hydrograph they synthesized for the 1% flood. So anything that is over that is going to spill out and go downstream through the highway. Okay, so frequency analysis is kind of like the basic, we're doing probability assessments and we're assigning, okay, well, the probability is acceptable for, we have a higher tolerance for probability of a failure, some kind of failure for lower priority infrastructure. And then we have a smaller tolerance for more important infrastructure. But we could actually calculate the risk based on design or analysis. And the idea of risk, we'll just call it R, we'll just say risk. Risk is, the way to calculate risk simply, at least from this kind of basic definition, is the probability of an event occurring times the consequence of that event. So probability, usually in terms of percent or fraction, consequence, usually in terms of dollars. So what is this? How would this calculation look? Say we have this design discharge that we're going to design to. We have a probability of that discharge occurring. So as we get a bigger discharge, the probability of it occurring goes down. And then maybe we need a consequence curve. Maybe the consequence curve looks something like this, where if we design the infrastructure to withstand a peak discharge of a given magnitude, the consequence is nonlinear, but it goes up. Obviously, if it fails with a bigger discharge comes, the consequence of failure is larger. So if we combine these two and kind of multiply them, maybe we get a shape, and I'm just going to make this shape up. It's not an actual shape, but maybe it looks something like this, where we've got a really high probability and a real low consequence. So we're kind of high right here. Then we kind of go down, and then maybe we start to increase our consequence. And so our consequence is minimized by a design somewhere around here. We would call this our minimum design capacity. So this would be the discharge associated with that. And maybe our peak consequences over here. But so maybe this is actually what we want to focus on. We say, okay, our minimum consequences here, we definitely need a design, use a design discharge above that. But our maximum consequences over here, and really that's where things could get bad. The road is going to be out for 3 weeks or a month or something like that, and it's going to, Interstate 70 is going to be closed. Oh, that just happened for 2 weeks. You know, I want to look up the economic impact of Interstate 70 being closed for 2 weeks. It's probably not small. So we can find the maximum consequence, and maybe this is where we want to think about actually designing, because if we avoid this maximum consequence, we're not doing the biggest peak discharge that's probable. We're not addressing the biggest consequence, but it's the maximum. It's kind of the integration of these two. We could also think about economic risk. This is taking another step. And so this would be a little bit more of an integrative approach. And so the idea of this is that we're minimizing the total expected costs. So we'd have annualized costs on the y-axis. We have maybe our structure size on the x-axis, which could also be the design discharge. And let's see. So as we increase the size of the structure, the costs increase probably non-linearly. Really big, maybe the incremental cost becomes much bigger. So there's probably a sweet spot in there. And then we have flood damages. So as the structure size increases, our probability of flood damages goes down. And then we can do those formulas that we know about how to annualize a cost over 20, 30, 50 years. We can come up with an annualized cost curve. Or expected cost, right? So maybe there's some sort of economically optimal solution to this. Okay. Let's take a stretch break and then we will continue our discussion. Okay, guys, there are, let's see here. Let's talk about one more kind of method, and it's called the critical event method. Doing green now. And the idea of a critical event is we sometimes have infrastructure that is too big to fail. Can you guys think of an example of that? What would be a too big to fail kind of infrastructure, Christian?
oversizing a dam or oversizing pretty much any infrastructure. I can't name an exact one, but
Yeah. You could think of something that if it failed, thousands of people are going to die, or the water supply for a city is in jeopardy, something like that, right? So we're typically talking about dams here. Dams are the kind of big types of infrastructure, pipelines that are just critical, right? If they fail, then all bets are off, and we're in a bad shape for the city, or the West, or whatever it is. So we typically want to design these structures so that there's just a fathomably small chance that they would ever fail, that a storm event could come that would overwhelm them and cause them to fail. And so there's two different ways to think about this. One is calculating the probable maximum flood, also known as the PMP. And then we also have the probable maximum precipitation. Sorry, this is the PMF. Can't spell. And this is the PMP. So this would be your nuclear power plants. Or your Hoover Dam. Or really any dam that is not just like some tiny thing. So high hazard situations. And
so like the pipes up in the north, like the Dakota.
I would like to say that you're talking about the gas transmission lines. Yeah, those are not designed for the PMP. No, probably a 100-year flood event in terms of scour or setback under when they cross rivers and stuff like that. Unfortunately, not, because yeah, environmental contamination is not considered as important. So yeah, yeah, it's actually galling. I've done a bunch of scour analysis for pipelines, and you know, you've got these crude oil pipelines that are like 3 feet under a major river. Like there's 2 spills back-to-back years on the Yellowstone River because the pipelines were scoured and broke from flood events. They just weren't designed well. They just weren't. We don't have very strict standards for that, unfortunately. I think because of those catastrophes, that things are changing. And then how do you calculate this stuff? It's in the reading, but the idea is you kind of look for a big data source, because what's the maximum flood event? Well, we've been observing rainfall and flood events for 100 years, 150 years maximum, not for very long. And so if you want to think about the most biggest flood event that's possible for a particular area, you have to have indirect data sources. So some ways people do this is they'll go back and they'll find what's called paleo floods. And so you can actually find in like the canyons in Colorado and areas, you can find deposits. Say this is a canyon somewhere. You can find scour lines on like the rock. You can find little sand that might be deposited in a little nook or cranny somewhere. And that tells you that water had been up there at some point in the last like 10,000 years, assuming that this bedrock really hasn't changed that much. So you can go back and survey that and then use a hydraulic model like HEC-RAS to figure out what the discharge is associated with that water depth in a particular canyon. And then there's some pretty complicated statistical methods to figure out the frequency of that or the probability of that event occurring. So that's one way you can do it. Another way is to just say, okay, what are for a given drainage area, what's the maximum discharge observable, you know, just in any watershed. So you have a database of the biggest floods in the world, and you create an envelope curve that basically align that is above all those points. And so then you could say, okay, well, the maximum flood event that's like even just possible no matter where I am for this drainage area is about this. That's kind of a rough way to do it. And then you could go back with precipitation, you could go to physics and you could just say, what's the maximum amount of precipitation we could get in a particular area based on the known aspects of the geography, the mountains, the water vapor in the air, and you can kind of model this and say, well, we don't expect to get more than, it's just not possible to get more than 24 inches of rain, you know, in a week or something like that for this particular area. So there's a lot of indirect ways to estimate these things. Okay, so let's think about design standards. It's going to be kind of the last part of this discussion. I'm going to go back to, let's do black. So hydrologic design standards are pretty much codified. You can go to the city of Grand Junction, and in their city code, they say culverts that go under a certain road, type of road, have to convey the 2-year flood events. And if they overtop, then they can only have, 6 inches of water for the 10-year flood event or something like that. So it's really prescriptive. And we can just look at some examples. So let's just talk about a bridge. So what kind of design standards might we have for a bridge? What would be the most basic design standard we'd have for a bridge? Edgar, what do you think? Say here's our bridge, and let's think about, here's the river and the valley. The bridge is going across. What might be some standards we want to know about to put into a design of a bridge across a river?
Probably how tall or distance you want, how tall you want it.
Yeah. Yeah, so this is our water, or we'll just say that right there. Yeah, so what's the elevation of the bridge deck? Maybe that's important because, well, we want to match the elevations of the road, the approach roads and that sort of thing. But it's also like these piers, how tall these piers are is going to be expensive. So we want to know, for example, if we're going to design this bridge for the 1% AEP flood, we want to know how much water, how much discharge that is, and then we'll do our hydraulic model to figure out how high that water is going to be. Okay, and then we'll want some freeboard there, which is basically a safety factor or a little extra space. I think it's freeboard of 1 foot or 2 feet or something like that. So we want to be able to convey the flow. So for bridges, we want to convey some design flow underneath. We want to avoid backwater. And the idea is if the flow approaches the bridge decking, I can back the water up. You might get overtopping, and you could destroy the bridge. We want to also think about pier scour. So this is kind of a little more complicated because the idea is for a certain flow event, you can actually scour the soil around the piers. If this is a pier right here, and if the piers only go so deep, all of a sudden you lose that pier, and then you get bridge failure. So there might be some design for pier scour. Say it's like, okay, it's okay if the bridge gets overtopped for a flood event that's bigger than the 100-year flood, but we want the piers to remain stable for, say, the 2.2% AEP flood. And so the bridge is overtopped, but the piers, the scour is not going to go down below the piers. We're going to dig them deep so that they're not undermined. And the bridge, maybe everything erodes away from the bridge, but because that bridge is so critical and expensive and hard to fix, those piers are going to be stable for a much larger event. Okay, so bridges, so there's my point here is that there's a lot of different components to infrastructure, and we might have different probabilities and different design standards according to that. Let's just talk about a culvert a little bit more specifically. So culverts, we want to convey a certain flow rate. Through the culvert. We maybe have an acceptable overtopping frequency. It's okay if the road's wet, you know, once every year or once every 5 years or something like that. But then maybe there's a maximum depth associated with that. So say the culvert needs to convey the 50% AP flood, and it can overtop with 6 inches of water at the 10% AP flood. And I don't know if this is the exact number, but this kind of design standard came out of the City of Grand Junction Stormwater Manual. And then maybe the road should be able to withstand scour. I'll say that, well, I should call this a crossing, a stream crossing. We'll call this the 2% AP flood. So it's okay if the road gets wet, but it can't be that deep. And it's okay if the road washes out, but maybe we're going to design it so that it doesn't wash out up to the 2% flood. This is not like a major highway or something like that. And let's think about what would this actually inform? So the design discharge, what component of the culvert is that going to inform? What design component? What's that? The diameter, yeah. So the diameter of the culvert itself, okay? And then how about the overtopping frequency? What part of the design could inform that? Yeah, so our roadway embankment elevation, but also, well, okay, so say we do a diameter that can pass this flood, but given the maximum elevation for the road crest, the 10-year flood is deeper than 6 inches. So maybe we need to go back and make a bigger culvert so that this 10-year flood is only 6 inches deep right here. Yeah.
To make the culvert deeper.
Typically, you're constrained by that because you've got this profile of the creek, and here's the roadway. And so the culvert usually has to kind of follow the topography of the ground itself. You don't have a lot of wiggle room with that usually, yeah. And yeah, maybe you can make this road crest taller, but often you're limited by that because you don't want like this huge hump, right, when you go over. And it's expensive to fill and that sort of thing. So these are all kind of trade-offs. What might you do to avoid the roadway washing out?
More material in your road, a type of material, or put something along that side of the road to prevent scouring.
Yeah. So just you could armor it, right? So you could put riprap in or energy dissipation so that when the flow goes over it, it's not going to just be hitting like sandy material or dirt or whatever. So you can kind of armor it up so that it won't wash. Okay. And then I will, the last topic, the last thing I'll talk about is, there we go, is this risk calculation. So the probabilistic risk calculation. And I will post these lecture notes and you can look at the derivation if you would like. But this came out of stats and I think it was the geometric distribution, which we covered last semester. But the idea is, if you want to, okay, so we'll start out with P. So P is going to equal to the probability of an event. So, you know, our 1% AP event. And so I'm calling this probabilistic risk because there's risk has multiple definitions. And I did that kind of risk is equal to probability times consequence, right? That's a little bit different here than this probabilistic risk calculation because we're only dealing in probabilities here. So P is the probability of event. R is going to be the probability of P occurring over n years. And so I'll just write the equation, then we'll talk about an example of it. So the equation is R is equal to 1 minus P to the n. And so R is simply the probability of seeing this event P occur over n. N might be like the design life of a structure. So if we want to, for example, say a bridge has a design life of 100 years. We got that old railroad bridge out there on near Fifth Avenue, or Fifth Street, going over to Orchard Mesa. I bet you that thing's over 100 years old. Still rocking. That's an old bridge. So say we got a bridge with a design life and the design discharge for overtopping was the 1% AEP. And assuming that number is still valid after 100 years, we'll talk about non-stationarity and how that number could change over time. What is the so we want to calculate the probability of overtopping over the, we could say next 50 years, over the design life. We'll just say design life. Can I go next page? All right, so first question is, I'll just write that equation out. R is equal to 1 minus P to the n. So what is P, Val? Yeah, and so for this example, what was that probability? Yeah. 1%. So 1% AEP. Okay. What was N for this? 100 years. So 100-year design life. Great. So let's plug those numbers in. stapled this wrong. That's what happened. So let's calculate R. R is going to equal to 1 minus 0.01 to the 100. Go ahead and give me a number when you get when you get it. Okay, so 63.4%. This number actually is going to be the same for any set of, say this was 50 years, and this was the 2% AEP. Or if this was, the design life was 10 years, and this was the 10% AEP. That number, I think, is, you can check that, but it should always be the same. It should always be 63%. And that's simply the probability of an event occurring. So if this is the AEP, 1 over 0.01 is equal to 100. And so the reciprocal of this probability is the recurrence interval. And if the recurrence interval is the same as the design life, then the probability of that event occurring within that design life is 63%. So that's just a constant number. So if we want to actually then calculate the risk, meaning probability times consequence, say of this bridge failing over its design life, say we say that bridge fails, and the economic consequence of that failure, because it's going to take 6 months to build it back, the economic consequence is going to be 50 million. Then what probability do we use to calculate this risk? We're going to use this, what we just calculated up here, so that probabilistic risk. So we'll use 63.4%. So
when you multiply that out, you still got a huge number, and that number is what now?
Okay, so 63.4% is the expected probability of the bridge overtopping over 100 years. And that I'm multiplying that by 50 million, which is the consequence of that happening.
So then you get like 31 million.
So that's the quote unquote economic risk.
Oh, okay.
It's kind of layered, right? You have the probabilistic risk, and then if you multiply that by the consequence, you get kind of we'll just say economic risk. You said that was 31 million. So it's like, okay, 31 million, what is that worth to us? Is that something that seems like a big number or a small number? That's just a number to kind of have to think about. All right, we'll stop it there.